All right. Hello, everyone. Welcome back to Math 261 this beautiful February 7th evening. Reminder that 1.4 and 1.5 homeworks are going to be due on the 7th. 1.6 homework is going to be due on the 14th because we will finish that section today. We will make a decent amount of progress in 1.7 as well, but we will not get to 1.8. 1.8 being the last section on test 1, which we should finish. I believe we should finish 1.8 next week. So test 1 on chapter 1 should be in 2 weeks. We'll talk in more detail about that next week. But for now, that is the plan. If that changes, then you will know next week. But keep that in mind. The test 1 will be in 2 weeks. We will still hold regular class on weeks that we have tests. As a reminder, you will take the test on your own time. I will give you a couple of days as an opportunity to take the test since you have to take it outside of the classroom. But you'll be taking that in my math lab on your own time, like a homework assignment, except for the fact that once you open it, you do have to finish it in one sitting. It's a no notes, no books, and this test will be no calculator, FYI. But again, we'll talk about that more next time. So I don't want to waste too much time. I do have exactly the amount of time we have worth of material to cover. In fact, I'm going to need to make our break only like 8 minutes instead of 10 today. So let's go ahead and get right back to the example where we left off last time when we were talking about the product rule for derivatives. So we had done a couple examples, and we're going to do one that's just slightly more involved now. So let's go ahead and get it. As always, if you have any questions, I'll be in the chat.
It's a give and take. All right, so I'm just going to go straight to the product rule. So I'm going to call the first, and I got to scroll down. The first is this parentheses, the x to the fourth plus the x squared plus 1. And then the second would be the x cubed minus x. So let's do the derivatives of those things individually. So the derivative of the first. The 4 is brought down. Then you decrease its exponent by 1. So that's 4x cubed. That's the derivative of the x to the fourth. For the x squared, you bring the 2 down, so plus 2. Leave the x alone. Decrease its exponent by 1. So I'll write the 1 fancy so you can tell it's a 1. Then plus, the derivative of a constant is 0. So there's a plus 0 here you can imagine, but I'm not going to write it. So that's just the derivative of the first, meaning that the derivative of the second, so we're looking at the x cubed minus x now. We bring the 3 out front. Then we have our x, and we decrease its exponent by 1. So 3 goes to 2. There's a minus symbol. And the derivative of x, this is a linear term, which means the derivative is its coefficient. Now you don't see a number written, and we don't see a coefficient. You know that it's supposed to be a 1. So the derivative of x is 1, but that's a minus, which makes it a minus 1. If you apply the power rule, it still works. If you start with x to the 0, then the derivative, if you start with x to the first, pardon me, the f prime, you'd have a 1 out front, then an x to the 0. So that's 1 times 1, which is 1. So that was just some side confirmation that we've done before. All right, now we didn't use f, we used y. So when I write the derivative, I need to write y prime, or I can write dy over dx. I could have been doing df dx before as well. Remember, I like to use both notations interchangeably because they mean the same thing. So again, when you're doing this, the main issue is to make sure in each term you've got something from the first and something from the second, where in each one of them should be a derivative and the other should not be. So if you do the derivative of the first in the first term, then the derivative of the second should be in the second term, or vice versa. There's a lot of freedom with the order you write things. I just like to be consistent for now, so I'll go. Once again, the derivative of the first times the second plus the first times the derivative of the second. So I'll do the derivative of the first and the derivative of the second and the second. So the derivative of the first, that's red, 4x cubed, red, plus 2x, I'm not going to write the first power. Then this is supposed to be times, but that's a binomial, so you better wrap it in parentheses. So since this was the derivative of the first, now I'm going to use the regular second. Now the second function is the x cubed minus x. So x cubed minus x. But again, multiple terms, so you better wrap it in parentheses. Then a plus symbol. So in this one, it went derivative of the first, so we better use the regular first this time. The regular first being this trinomial, x to the fourth plus x squared plus 1, and we're going to multiply it by something else, and to make sure all three terms get multiplied, parentheses. Now we use the regular first, so for the second, it better be the derivative. That was this, the 3x squared minus 1. Multiple terms, wrap it in a parentheses. Theme of the day. Now, unless this is just super chaotic and crazy looking, you generally need to simplify this as much as possible. Sometimes you can factor. It could be a GCF, it could be other stuff. That says GCF, comma, etc. That got a little slot because I ran out of room. Your GCF can be a binomial or a trinomial. That is always a possibility, so look out for that. If this parenthesis, if one of these parentheses was an x minus 7 and then this thing had a parentheses x minus 7, you could take it from both of them to make this much simpler. I don't really see anything like that happening right now. You can take some x's from each of these parentheses, but not these. So let's just stick with this. Y prime equals, let's FOIL the first red and black. So 4x cubed times x cubed would be 4x to the 6th. Remember, you're adding exponents. Then 4x cubed times negative x would be a minus 4x to the 4th. Then the inner, 2x times x cubed, would be a plus 2x to the 4th. Then the last, 2x times negative x, would be a negative 2x squared. You have got to be on top of those simple algebra rules. If you don't have those, you can't do calculus. Calculus is easy. Calculus is just memorizing the formulas. The rest of it is entirely algebra. No one fails calculus because of the calculus. They fail it because of the algebra, because they don't learn the pre-calculus stuff, because they wait 4 years to take this class, because they don't want to practice. So again, that was just foiling the first parentheses. Let me pick a different color to show the distributing of the second. So I can only call this distributing the x to the 4th, the x squared, and the 1 to the 3x squared and the negative 1. It's 6 products. If you got 3 terms and 2 terms, it's 6 products. If you had 3 terms and 4 terms, it'd be 12 products. It's a number of terms times the number of terms. All right, so distributing the x to the 4th, I'll focus on this one first. That's a plus. X to the 4th times 3x squared, that's going to be 3x to the 6th. Then x to the 4th times negative 1 is a minus x to the 4th. Now I'll focus on, oops, that was weird, the x squared. And I just learned a trick. If I hold this button down and hover over stuff, it erases, for better or worse. I don't know why it worked before and now it's not. Okay, I'm still figuring out my pen if you can't tell. All right. So now let's distribute the x squared. X squared times 3x squared, that's going to be a plus 3x to the 4th. X squared times the negative 1 is a negative x squared. Now let's distribute the 1. 1 times anything is the anything, so that's plus 3x squared minus 1. And at this point, we can combine like terms. CLT, combine like terms. So we get y prime equals 4x to the 6th plus 3x to the 6th is 7x to the 6th. I'm going to squiggle the ones I've used. I don't want to cross them out. So 4x to the 6th, where is it? Plus 3x to the 6th gave us that. Then our x to the 4th. So I don't have any x to the 5th. So the x to the 4th, we got a minus 4x to the 4th plus 2x to the 4th minus x to the 4th plus 3x to the 4th. We've got 4 of them. And we're just going to combine the coefficients. So that's a negative 4. Sorry, my eyes went cross for a second. That's a negative 4 plus a 2, which is negative 2. So we're done with these two. We've got a negative 2. Then we got another one here that's a minus, that's -3. Then we got another one here that's a +3, and -3 plus 3 is 0. So in fact, all of the x to the fourth terms cancel. -4 plus 2 minus 1 plus 3 is 0, if you check that out. So there's no x to the fourth term. For the x squareds, there's no x cubed, so we got a -2x squared minus 1x squared, so that's -3, plus 3, -3 plus 3 is 0, so there are also no x squared terms. And we're done with everything except the -1, so here's the -1, bring it down, there's nothing to combine, so that's our derivative. dy dx, or y prime, however you want to write it, is 7x to the 6 minus 1. Now, I'm not saying whether this problem is easier or not if you do the product rule, then simplify, or if you simplify, then do the product rule. Sometimes it's easier to simplify first. Sometimes it's easier to do the product rule first. It depends on the problem. This one, honestly, it goes either way. Me, having done hundreds of these, I would argue it's better to do the multiplying first, but that's not always easy to do. And we'll see that in the next problem. So you could, on your own, go back and do that blue do you trust it stuff and go ahead and multiply this sixth products initially, then do the power rule. I think that's easier, but it's about the last time that I would say that. So for D, which is my C, f of x equals, parentheses, x cubed plus square root of x, those are always fun, times 3x squared minus 5x plus 2. Okay, so if you're going with this whole first and the second thing, and how you write things out doesn't matter to me, but I'd call the x cubed plus the square root of x the first, and then I'd call the 3x squared minus the 5x. What am I doing? I'm talking and writing at the same time. The 3x squared minus 5x plus 2, I'd call that the second. So when you go and take the derivatives of those things, if you think about them as their own quantities, the derivative of the first, well, this one's going to be a little bit more work because of the square root of x. So when we take the derivative of x cubed, that's going to be 3x squared. The exponent goes out front, and then it decreases by 1. Plus, now the derivative of the square root of x, we did this last class. It turned out to be 1 over the square root of x. I'm sorry, 1/2. 1/2. There's a 2 in the bottom. I want to clean that up a little. 1 over 2 square root of x. If you need to see that one more time, I'll do that over here. If f of x, if y equals the square root of x, which is x to the 1/2, then y prime would be 1/2 times x to the negative 1/2, because you're doing 1/2 minus 1, which is 1/2 minus 2 over 2, which is negative 1/2. But you don't like negative exponents, so you bring it to the bottom. That's 1 over 2 x to the positive 1/2, which is 1 over 2 square root of x. So that's where this came from. The last part of the first derivative came from all this blue stuff over here. Again, the negative 1/2, that came from this, just doing fraction subtraction. All right, so back to the second. Let's do the derivative of the second, which will be significantly easier. So the derivative of 3x squared, we're going to leave the 3 out front, drop the 2 down, and then decrease the exponent by 1. That's going to give us 6x. So I'll write something that I'm going to erase. I don't want to take up the whole area for this, but we had the 3, then the times. We bring the 2 out front, we have our x, and then the exponent drops to a 1. But the 3 times the 2 is 6. So that 3 times 2 times x becomes 6x. Then we have the minus 5x term. That's linear, that's a special case. So the derivative is just the coefficient, it's just the minus 5. Minus 5. Then for the 2, that's a constant, that's the other special case. The derivative of a constant is nothing. That's a horizontal line. Horizontal lines have a slope of 0. So that's the second derivative. So in terms of thinking about the functions as a first and a second, in terms of a product, here's the derivative of the first part, here's the derivative of the second part. So now what we can do is say, so f prime of x, the derivative, df dx, if you want to, df dx, just giving you both notations again. Formula, the variation I like for now, derivative of the first times the second plus the first times the derivative of the second. So the derivative of the first is the 3x squared plus the 1 over 2 squared of x. 3x squared plus 1 over 2 squared of x. Multiple terms, so wrap it in parentheses, times. So that was the derivative of the first times, now we're going to use the regular second function, not the 6x minus 5. Pay attention. It's the trinomial, the 3x squared minus the 5x plus 2. Multiple terms, so wrap it. Then a plus symbol. Derivative of the first times second. Now flip-flop it. The first function being the x cubed plus square root of x. Multiple terms, so wrap it. Then times the derivative of the second, which is the only thing we haven't used, the 6x minus 5. Notice we use all of the bits. First, second, derivative, first, derivative, second, all 4 of those things get used. You just have to have them in an appropriate order. And again, there's like 8 or 16 different appropriate orders that would work. This is just a particular way I do it. And the only reason I do it this way is because it's the way the textbook likes to do it. Actually, that's a lie. I'm doing it the way the old textbook likes it. This textbook does it derivative of the second, then derivative of the first. Doesn't matter. It really doesn't matter. Now, you can arguably clean this up. And if this was a regular calculus class, that's something that I would emphasize. For now, let's just say this is the answer. So while you can clean this up, let's leave it for now, which is also what your homeworks do. Your homeworks are allowing you to leave square roots and bottoms. They are allowing you to leave products like this for more complicated answers. So for now, we're just going to leave this alone and say that's the answer. Because this would be a significantly more challenging problem if we actually go through and distribute these 6 products, FOIL these, clean up, rationalize the denominators to then combine terms that we can combine with. You're multiplying an x squared with square roots, so you have to go back to the rational exponent forms. It's just a bit of a mess for now. So like I said, we're going to leave it alone. You also, it may be acceptable to write this version, and I'll do it in blue. I have seen problems where it's okay to write 3x squared plus 1/2 x to the negative 1/2 times 3x squared minus 5x plus 2, then plus x cubed plus x to the 1/2 times 6x minus 5. I have seen our homework. I've been diving much deeper into it to make sure I can relate things to y'all. I've seen problems where they're letting answers have rational exponents. So what I'm saying is my math lab should take either of these versions, even though I definitely have a preference. I definitely prefer the top version versus the blue version. But it is what it is. So just make sure that you're able to get the answers right in your homework, because if I do a test that's MyMathLab based, which I will be doing, I just don't know if I'm going to do all of them that way, then you have to understand what MyMathLab prefers. You practice in the homework to then know what the test wants. Okay. So that's our product rule. We spent a solid amount of time on that. That's half the name of the section. The other half of the name of the section was the quotient rule. So we should probably talk about the quotient rule. Product rule is for products, the quotient rule is for quotients. So given a function expressed as a quotient, in other words, a fraction, a fraction. And let's say that it's originally written as f of x over g of x. And again, you can also just say first over second. That is definitely what I prefer to say. The derivative of this quotient, the derivative of this fraction. So this is us to saying take the derivative of the f of x divided by the g of x, or the first divided by the second, or just f over g. You don't have to have the function dependency, as we've said. Now I'm going to go ahead and say out of the gate, warning, 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 warning. While there was a lot of different ways you could write the product rule, you could interchange the first terms with the second terms. The main issue is just making sure you had a derivative in the right place and a non-derivative in the right place. You don't get as much pliability here with the quotient rule, and that's because there's a minus between them instead. So it's going to be a blah, blah, blah minus blah, 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 which says these two things are not interchangeable, so you have to get used to this. So the way I like to write this is g of x times f prime of x minus g prime of x times f of x all over g of x squared. Once again, you have got to memorize this rule. So some alternate ways. If I just say the d dx of f over g, I could write g f prime minus g prime f over g squared. Or I could write, what's my favorite? G times f prime, the second times the derivative of the first, minus the first times the derivative of the second over g squared. So I'm going to put a little circle around my favorite version. It looks really close to the black one, the black version, but I swapped the order of the G and the F. What in the heck did I write there? Something's wrong. Please forgive me there. I had this squared in my head a little too soon. G F prime minus F G prime. So that's my favorite way, which in terms of first and second, so if you say the derivative of the first over the second, that would be the second times the derivative of the first minus the first times the derivative of the second, all over the second squared. Some people might say it doesn't make sense to call them first and second when it's top and bottom. It makes more sense to do it that way with a product. You know what, I kind of get your argument, but it works either way. Instead of using first and second, guess what you could say instead? Top and bottom. So you could say, scroll down a little, d dx of top over bottom, I'm just going to abbreviate with T and B. It's going to be the bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. I don't care how you're memorizing these rules. I care that you're able to have a version that you're used to and that you can get answers correct with it. So again, the typical way I'm going to be saying things is like this. The only things you can really swap are, in this first term in the top, you can swap the order of the derivative of the first and the second. And that derivative looks a little thick. Let me just make that prettier. So you can swap the second and the derivative of the first, you can swap the first and the derivative of the second, but you can't swap anything from before the minus with anything after the minus. That's the major difference between the product rule. There's a lot of room, there's a lot of wiggle room in the product rule. There's very little wiggle room in the quotient rule. And the bottom is always the bottom squared. And once again, you're taking this as a leap of faith without me deriving anything. Go to the internet, go to your textbook if you want to see derivations. But again, this is not a theoretical calculus class. This is an applied calculus class. So we are where we are. Example. What do we have to example 2? Yes, we are. Guess what we're going to do? Find the derivative. Using the quotient rule. And we will start out with an example that we can verify it works. X to the 8th, it's an ugly 8, over x to the 2nd. So we're going to do this with our new rule, and then we'll do it again in a much simpler version, and you'll go, why would we ever use the quotient rule for this problem? And I would agree with you. I would never do the quotient rule for this problem, except in the situation of showing that it works. So let me call, again, I like first and second. If you like top and bottom, just the bottom is the second. So I'm going to call the x to the 8th the first, and the x to the 2nd the second, which makes the derivative of the first, take the 8 out front, decrease its exponent by 1, and that makes the derivative of the second, take the 2 out front, and decrease its exponent by 1. And again, I'll write the 1 all fancy so you can tell, but I won't write it anymore after this. So we got our top, our bottom, a derivative of our top, a derivative of our bottom. Those are the 4 pieces we need. All those 4 pieces go on the top, and then there's just an extra bit in the denominator. The denominator happens to be the original denominator squared. Okay, so f prime of x. And I'm going to be using, again, this is my favorite. So the second, aka the bottom, times the derivative of the top. The first term has to have the derivative of the top. The second term has to have the derivative of the bottom. That is how I managed to memorize these when I was taking calculus back in, I won't say when. Long time ago. The first term needs the derivative of the top, or the first. The second term needs the derivative of the second, or the bottom, however you're calling them. That was not as critical back in the product rule. The derivatives could go wherever you wanted them as long as it was a mix and match. The quotient rule, it's critical. The order is critical. Okay, so the second, or the bottom, that was the x squared, so that's going to be in black. So here's our bottom, or second, times sorry, I've got something going on. I'm watching my dog to make sure nothing's about to happen. Might be TMI, but I've got an old dog who has really bad nosebleeds sometimes for literally hours on ends, and He's behaving like it's about to happen. So I'm sorry that I'm distracted, but I don't want my carpet to get super bloody. And if that grosses you out, sorry for the TMI, but that's life. Okay, I'm going to move on. He's next to me at least. Okay. All right, so we had our second or bottom, whichever you prefer to call it, then times, that's supposed to be the derivative of the first. And again, you can put the derivative of the first before the x squared or after. The order of the black and red won't matter for this term. The derivative of the first being the 8x to the 7th. Then we have our minus symbol. So again, the black and the red here are interchangeable. This is just a way I like. That's how I've always done it for some reason. It is what it is, minus. Now the opposite. So we used this and this. Sorry, we used this and this. We use these two. So we'll need the x to the 8th and the 2x to the first this time. So we have our first, which is the x to the 8th, times the derivative of the second, or the derivative of the bottom, which was the 2x to the first. But then we have the fraction bar. Don't forget this. The quotient rule is literally a quotient. And then it's supposed to be the bottom squared, the x squared, but then we have to square that. Generally, you're going to need a parentheses for that. So again, the thing inside was the original bottom, but then we have the parentheses squared that's part of the formula. That says the bottom squared. So the original bottom squared. And then we can clean this up. So x squared times 8x to the 7th is going to be 8x to the 9th minus x to the 8th times 2x would be 2x to the 9th, and over. X squared squared, we just multiply the exponents and you get x to the 4th. Yes, you get the same thing if you add them, but that's not the rule. If this was an x cubed being squared, this would be x to the 6th, not x to the 5th. Make sure you know your exponent rules inside and out. There is no excuse in a calculus class not to know your algebra rules. It's kind of like when you go to driving school and then we put you on the road, you're on the road now. You got to know the rules of the road. Algebra being the rules of the road. And we can clean this up. We can combine the top. So our f prime of x, 8x to the 9th minus 2x to the 9th is going to be 6x to the 9th. Then the bottom is just still our x to the 4th. But we can clean this up. We can subtract the exponents. 9 minus 4 is 5. Again, know your exponent rules inside and out. So this is our answer. So f prime of x ends up being very simple, just a 6x to the 5th. That's our derivative. Quotient rules are usually not this simple of an answer, but that's because this problem was not designed to be done with the quotient rule. It's meant to prove it works. So now let's go and say, I don't trust you. I'm not taking the leap of faith. You just gave me a formula. Do you trust this? So let's go back to the original function, which was x to the 8th over x to the 2nd. You can simplify that. Top and bottom, subtract the exponents, you get x to the 6th. No more quotient rule needed, just a power rule, which means our f prime of x, take the 6 out front, leave the x alone, decrease its exponent by 1, and you get 6x to the 5th, which is the same thing. It worked. Now, when you look at the blue, you can tell why your teacher on his own would never, ever, ever do it the other way. I would have definitely simplified this first and then applied the simple power rule, because when you simplify it, it breaks down amazingly. But guess what? Not all fractions are going to simplify this greatly. You're going to be mainly looking at things that have multiple terms in the top and the bottom, which complicates things and makes the quotient rule necessary. So while there are a lot of problems that you can get out of doing the product rule by pre-multiplying, there's not a lot of problems that you can avoid the quotient rule on. So it's kind of ironic that the more complicated formula is the one that you arguably need more. And that's, again, because the product rule can be avoided in a lot of instances. So this is definitely a more complicated rule. Let's practice it some more. Wrong color, not that it technically matters, but I want consistency. B. So let's go with an original function of x squared over x plus 1. So this is a much more common type of problem. Okay. So whether you're calling them top and bottom, whether you're calling first and second, whether you're just going to call them f and g, even though we call the original function altogether f, I mean, it'll work, but I'd be careful skating on that thin ice. It's not really appropriate. So the first, or the top, whichever you prefer to call it, would be the x squared. And the bottom, or the second, again, whichever you'd like to call, would be the x plus 1. Let's take those derivatives individually, which they're pretty simple functions, so it's easy to do the derivative of the first, or top, 2x. It's about the 50th time we've seen that one already. And then the derivative of the second, or the derivative of the bottom, depending on how you like phrasing. The derivative of x, there's an imaginary little 1 in front of it. That's a linear term. The derivative is the coefficient. So the derivative of x is 1. Then plus, the derivative of 1 is 0. So again, it's not really necessary to write plus 0. The derivative of the x was the 1. The derivative of this 1 is 0. Those are those two special cases that you'll see over and over and over and over and over. So really, I just want to write the derivative of the second as 1. And that's derivative doesn't look too great. There we go. And again, you could have been labeling these as t, b, t prime, and b prime. Nobody cares. It's all about understanding the formula, memorizing the formula, putting things in the right place. I just don't want to clutter my screen too much. So that tells us f prime of x, the derivative of this original function. If you forgot the rule, here it is. Again, I like this version. All the black and blue versions work, no matter what you're calling them, how you're labeling them, the order you do things. So I like second, then derivative of the first, minus first, and derivative of the second. So the way I like it is just I like the regular functions to be the first, and then the derivatives to be the second in each of the terms. I think my calculus teacher back in high school just always did things that way, so it stuck with me. Regular function in the first spot, derivative in the second spot. It's also how I do my product rules, in fact. I'm gonna So when I go back and do my product rules from now on, you'll actually notice that I use the same pattern. And the reason for that is so I don't have a pattern for the product rule and a pattern for the quotient rule. That way I just memorize the quotient rule and remember that the product rule has a plus here instead and no bottom. That's it. Cough attack, dry air, allergies, all the fun stuff. Okay, so again, second derivative of the first, first derivative of the second. So second is the x plus 1. So I'll do that in black. Multiple terms of parentheses, times. Then the derivative of the first, which is the 2x. So again, my pattern is regular function derivative, then the minus, regular function derivative. But it has to go. It has to be the derivative of the first in the first term, derivative of the second in the second term. You swap it and it's wrong. Okay, so the first, which would be the x squared, and times the derivative of the second, which was down here, the 1. You should be using all 4 bits of the first, second, derivative, first, derivative, second, top, bottoms, whatever you're calling them. The bottom is now the original bottom squared. The original bottom was x plus 1. Because it's got multiple terms, you got to wrap it into parentheses. I did in the last one too, even though it's arguably not necessary. But rule of thumb is you should probably have that bottom in a parentheses before squaring it. Now, what we will generally do, we clean up the top only. Generally, I'm not saying there aren't problems where we don't do something with the bottom. That's just usually what we focus on. So we get f prime of x equals. The 2x can be distributed to the x and the 1, so 2x times x is 2x squared. Then 2x times 1 is a plus 2x. Then we have a minus 1 times x squared is just minus x squared, all over the bottom, which is x plus 1 squared. Back when we were dealing with rationals in pre-calculus and in algebra 1, algebra 2, whatever you had, we usually didn't mess with denominators very often once they were factored. And this is factored. So I don't really see a need to do anything with that unless maybe the top turns into a matching factor that can be reduced. But yeah, you're generally not going to expand that bottom. All right, well, there's like terms, 2x squared minus x squared, that's 2 minus 1, which is 1. So that's just a 1x squared, then the plus 2x, and then over the bottom, which is x plus 1 squared. That's it. That is our f prime of x. That's our derivative function. That's the function that dictates the slope of x squared over x plus 1. Now, I can't go through and verify this one, unfortunately. I can't do the blue stuff because this is a more complicated rational function than that one. It's above our pay grade in terms of trying to go ahead and divide this ahead of time up front. You'd need long division, which you were taught in pre-calculus. But then the last term is still going to be a rational function of over x plus 1. And there's a way that you can bring that x plus 1 to the top and do a power rule, but it needs something called the chain rule, which we haven't done yet. So I can't verify this one. You got to trust me. But hopefully, since the last one worked, hopefully you gained my trust with A enough that you know that B, you trust me that B is correct. So let's do another one. F of x equals x cubed minus 1 over x plus 1. So once again, good idea to label first and second or top and bottom. I'll do top and bottom this time just to mix things up. So I'll call the x cubed minus 1 the top, the x plus 1 the bottom. So then the derivative of the top, this is just a polynomial, no product. Now imagine if you had products and quotients inside of a top or inside of a bottom, that would make things even worse. It can happen. I won't do anything like that on a test necessarily, but you can mix products and quotients in a simpler way in a homework problem or a test problem. I'm saying I wouldn't have a product inside of a quotient necessarily. All right, so the top derivative, bring the 3 out front, decrease the exponent by 1. So that's the derivative of the x cubed. Then we have the minus 1, that's a constant. The derivative of the constant is 0. Then our bottom derivative, the derivative of x, I mean, it's literally the same as last time, so we should know it's 1. But the derivative of x is 1, because there's a coefficient of 1. The derivative of 1 is nothing. So there's our top and bottom derivatives. We have our top derivative, and our bottom derivative. That's the 4 things that go into our formula. So f prime of x is equal to. So we're going to do, again, the main issue is, in the first term needs to be the derivative of the top. It doesn't matter if it goes first or second in the term. But again, in front of this minus, you need to have the derivative of the top and the regular bottom, whether they go first and second or second and first, it doesn't matter, but it has to have the derivative of the top here before the minus. So I'm going to go bottom, which is x plus 1, times the derivative of the top, which was the 3x squared. You can put the 3x squared, then the x plus 1. That's okay. That's what I was emphasizing. Then the minus, that's not a fraction bar, just an emphasized, overemphasized minus. Now, because we use the derivative of the first or the derivative of the top here, we're going to flip-flop and do the derivative of the bottom or second in the second bit after the minus. So I like to go the top, which is black, x cubed minus 1 times the derivative of the bottom, which was 1. Then all over the bottom squared, which is x plus 1 squared. Okay, we can clean this up. The 3x squared can be distributed to the x and the plus 1. So that's going to be 3x cubed plus 3x squared. Distributing a 1 to something does nothing, but there's a minus that needs to be distributed. So what's going to happen is the x cubed and the minus 1 are going to change signs because this was a minus in front of it. So that's now a minus x cubed and a plus 1. This is where people make simple mistakes. They don't distribute negatives. They don't pay attention. And the bottom is still our x plus 1 squared. Again, the bottom is generally not going to get simplified. So f prime of x equals the 3x cubed minus the x cubed. Remember, no number in front of it means a 1. 3 minus 1 is 2. So 3x cubed minus 1x cubed is 2x cubed. Then we have our plus 3x squared. Then we have our plus 1. That's the entire top. We were only able to crunch together a pair of terms, and the bottom is x plus 1 squared. This is our derivative, as simple as it can get. And as I noted earlier, maybe the top can be factored to then reduce the whole fraction. Maybe. Sometimes it can. If it can, then do so. If it can't, then don't. That's going to have variability from problem to problem. Okay, so we've gone over our product rule, we've gone over our quotient rule. I've emphasized 10,000 times already the need to memorize them. You are not going to pass that first test if you don't know the definition of the derivative based on the limit. You're not going to pass this test if you don't know your power rule and the special cases for a constant and a linear term. You're not going to pass this test if you don't know your product and quotient rules. I mean, you could probably miss the quotient rule and still pass, but you're not going to pass well. You could probably pass this test without knowing the definition, but you're not going to make an A or a B. You need to know all of those. These are the things you have to memorize: the definition, the power rule and its two special cases, the product rule, the quotient rule. You've got to know how to use them. You've got to go to the homework and do this stuff. You're not going to learn it by watching me do it. That's how you pick up on things, but then you have to regurgitate it. You have to do it yourself. And if you do your homework and you get 100 on it and you still don't feel like you know it, go back and hit similar example on those homework problems. It'll keep your green check mark, but you can try it again and it'll be a similar example. Not the same, but close. Go to the textbook. Look at the homework problems. Find ones that are similar to what you did on your homework. Find ones that are similar to what I do on the lecture. Again, the problems in the lecture are going to be comparable to the test in general. All right, so let's get into kind of a side bit of information, but it all relates. It's something I did talk about a little bit in the last section with marginals. So remember that for given cost, revenue, or profit functions, which are C of x, R of x, and P of x respectively, they're, with an IR, their marginal derivatives, or their marginals, which are marginal cost, revenue, profit, are the derivatives. Marginal cost is C prime of x. Marginal revenue, R prime of x. And marginal profit is P prime of x. As a reminder, profit is revenue minus cost. P of x is R of x minus C of x. Cost is how much you spend to make your items, to sell your items. Revenue is the money you get at the stores for selling your items. Profit is the difference of what you make and what you spend. So if it costs you $1,000 to make a whole bunch of items, then you sell it for $2,000. That means your profit would be 2,000 minus 1,000, which is 1,000. Buy for one, sell for two. Classic way of making money. Doesn't mean your profit has to be that way. Maybe you spend $1,000 on your items, you sell them for $1,200, and then your profit's $200. Profit for a lot of businesses tends to be in like the 20 to 30% ballpark. At least when you're talking when you're talking accounting profit. When you talk economic profit, that's another story. And we don't dive too heavy into economics and accounting information in here, but we do glance at it, especially with things like this. So for an example, example 3. Let's say a business has a cost model C of x is equal to x plus 7. And a revenue model of why did it put it over there? There we go. Cool. Let's go with x squared minus 10x, sorry, negative x squared plus 10x. I have my signs backwards. Plus 100. Find the profit function. Then all 3 marginals. So maybe we're selling CDs, maybe we're selling hay, maybe we're selling owl figurines, maybe we're selling glasses. I don't know. All I know is we got a cost function, we got a revenue function. We want to find the profit function, then we want to find the marginals. And we're not going to do any crazy extensive information with them. We're not going to get into optimization. We'll save that for a later chapter, but we can at least start this idea. So your cost function is 5x plus 7. Your revenue function is this negative x squared plus 10x plus 100. We want to find the profit. Well, P of x, we already said, is the difference of revenue and cost, R of x minus C of x. I'm just going to go to my pen now. So the revenue function was negative x squared plus 10x plus 100. That's our revenue function. So then a minus. Then our cost function is this 5x plus 7. And I hope that everyone would instantly recognize that this is not correct, because to subtract the cost function, if it's got multiple terms, it's about the 10 millionth time we've needed extra parentheses here. So we can distribute that negative, which gives us negative x squared plus 10x plus 100 minus 5x minus 7. And then we can combine our like terms to get our profit function, which is negative x squared. The 10x minus the 5x is going to give us a plus 5x. And then the 100 minus the 7 is going to be a plus 93. Now, again, I have no sense of reality with this, with these models here. I just kind of made them up on the fly. If you wanted to say find the profit at 0 items sold, it wouldn't make sense because you'd find that you're making $93. Maybe you're doing that through tax cuts or something like that. You know, whether it's cheating the system or completely legal. but it is unusual to produce. If I put 0 for the x being the number of items, I'd get 93 here. It doesn't quite make sense, but again, this is just giving us an idea of how these fly. So there's our profit function. That was only the first thing. We also wanted all the marginals. So now that we have cost, revenue, and profit, we can do all three marginals. The derivative of cost would be the marginal cost. Well, that's 5x plus 7, just take its derivative. The derivative of 5x is 5, because it's a linear term, special case. The derivative of 7 is 0. So that's it. So this is our marginal cost. This is the cost to produce the next item. So in other words, if you want to, if you know the cost to produce 50 items, if you want to find out, well, what's the cost just to produce the 51st item? It's this thing where you'd plug 50 into it. You would plug, if you want to find out the marginal at 51, you plug in 50. There's actually nothing to plug in here, which says the next cost is always $5. It's going to cost you $5 to make the next CD, or $5 to make the next figurine, whatever we're talking about. For our revenue, R prime of X, it's an ugly R, but it's an R. Taking the derivative of negative X squared is going to give us negative 2X. Excuse me. The derivative of 10X, so that's a plus 10 because it's a linear term, so we just drop the X. And then the derivative of 100 is 0. So this is the marginal revenue. And again, this might not necessarily make sense, but that's not the point of this. So that's the cost to, I'm sorry, that's the money we would take in, not cost. That's the money we would take in from the next item. So if we want to say, well, all right, if we have this as our revenue, how much revenue will the first item bring in? Well, you'd plug in a 0 to find out the marginal at 1. So 2 times 0 is 0 plus 10, you'd bring in 10 for the next one. All right, well, how much does the second item bring in? You'd plug in 1. Negative 2 times 1 is negative 2 plus 10 is 8. So the second item would bring in 8. The third item would actually bring in 6. It's decreasing each time. And again, this is not necessarily typical to decrease that fast for a standard thing in the real world. We're just getting an idea. And then the marginal revenue, excuse me, the marginal profit. That's the derivative of the profit function, which was this thing. That would be negative 2x plus 5. The derivative of the negative x squared gives us the negative 2x. The derivative of 5x is 5. The derivative of 93 is 0. So this is the marginal profit, which actually states that we're only profitable for a short term because this term is going to keep growing in the negatives, which means we'd be losing money. So it sounds like we would need to grow our business to become more profitable and change our business model, which would change our equation models. Maybe we need more employees, maybe we need a bigger space, maybe we have to change how we network, I don't know. But this is how we get the marginals. So if I give you a cost or revenue function, you build the marginal by taking derivatives. That's not the only type of marginal we study, though. We also study marginal averages. Well, hold on. Before I get into that, let's talk about the average first. I haven't done the average with us. I was thinking I had, but I haven't. The average, whether it's cost, revenue, or profit function is, if you're using cost, it's C of x divided by x. Let me write that a little cleaner. C of x divided by x. That would be the average cost. The average revenue would be R of x divided by x. And the average profit would be, guess what, P of x divided by x. So again, with real business models, linear costs, revenues, and profits generally don't exist. If they were linear, then all these averages would be the exact same. It would cost you $5 to produce the first, $5 to produce the second, $5 to produce the third. So the average cost of each of them would be 5. But in the real world, we usually have what we call a descending average. So the more we make, the lower the average cost is of each. So it might cost you $5 to make the first one, but it only costs you $4 to make the 10th one. And it might cost you only $3 to make the 100th one, and maybe only $2 to make the 2051st one. So your costs are hopefully descending as you make more and more in terms of a unit cost. So what is an average? You add up the number of things and you divide by the total number of them. X represents the total number of them. That's why we just take the original function and divide by X. So these are our average costs. These are our average revenues. These are our average profits. But there are also, as I already spoiled earlier, marginals on these things. So let me go here. Let me just push this down, actually. There we go. So the marginal average cost or revenue or profit function is. And I'm just going to spoil this in parentheses up here. Take the derivatives of the previous line. So your marginal average cost is d dx, the derivative of the average cost. Or your marginal average revenue is the derivative of the average revenue. Or your marginal average profit would be d dx of the profit function divided by x. Again, you just take the average functions and do the derivative. But what's important here is that you understand that you do the average, then the derivative, not the derivative, then the average. If you do the derivative and then divide by x, that is wrong, 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 wrong. You have to find the associated average cost first, then you have to go and do the marginal. These are often represented with bars. So your average cost C bar, C bar over X, I'm sorry, C over X is generally called C bar. So it'll look like this. Or the average revenue function would be R bar, or the average profit function would be P bar, which would make the marginal ones C bar prime of X, or R bar prime of X, or P bar prime of X. That's the notation for your averages. A little bar over the letter means it's an average. A little 1 next to the letter means it's a marginal, it's a derivative. So average is a bar. A little 1 that looks like an exponent or a single quote tells us marginal, tells us derivative. So again, you have to do the average, then take the derivative. I'm gonna highlight that bad boy. That's how we find our marginal averages. And sorry, my other folder with my next example is somewhere else. Give me about 15 seconds. Here it is. Okay. I'm on draw, that's why. So example 3. No, example 4. Yes, example 4. Because I typed the last one, it threw me off. Where I wrote example, that is to say. All right. Printing on demand is a recent development in publishing that makes it feasible to print small quantities of books, thereby eliminating overstock and storage costs. For example, a typical 200-page book costs $18 per copy with fixed costs of $1,500. Therefore, using a fixed plus variable model, C of x is equal to 18x plus 1,500. I've mentioned this in passing that a lot of cost models are based on a fixed cost and a variable cost. So we have a fixed cost of $1,500. So they just say, all right, you got to pay $1,500 for us to do this at all. But then every time you want a copy, we're only going to charge you $18. So you pay $1,500 upfront for consultation, setup, blah, blah, blah. But then after that, if you want one copy, you pay another $18. If you want 100 copies, you'll pay $18 per copy. So $18 per copy means 18x. So this is the variable cost, 18 times the number of copies. So this is where x is the number of copies. Number of books, number of copies, whatever. What we want to do is A, find the average cost. B, find the marginal average cost. C, find the marginal average cost at x equals 100 and interpret. Oh, why are you doing that to me? Word annoys me sometimes. We'll do it this way then. Okay. So we have our cost function. Now, I don't have to give you this. Setting up a standard fixed variable model is something I expect of my Algebra 1 students. So that should let you know I expect calculus students to be able to handle a variable cost and a fixed cost to set up a standard linear model. If we have a nonlinear model, I give you the function. And I still give you the linear model most of the time, but I do reserve the right to not give you that cost function. So part A, find the average cost. So I didn't ask for just the marginal cost. The marginal cost would be 18, which says it always costs $18 to produce the next unit. That makes sense. It says right here it costs $18 to make each next unit. So for part A, we are finding the average cost, which is C bar. That means average, which is where we take the regular cost and divide it by x. The regular cost being 18x plus 1500. And then we divide that by x. Let me write it a little cleaner though. I don't know why I got so ugly all of a sudden. Come on, thank you. This is our C bar. This is our average cost function. So if you produced 0 units, you'd plug in x equals 0, and your average cost would be infinite because you'd be dividing by 0. If you produced 1 unit, then your average cost would be $15.18. So it's costing you $1,518 to make 1 unit. If you produce 2 units, 2 times 18 is 36. 36 plus 1,500 is 1,536. And then the bottom's 2. So what's that? 1,536, half of that would be what, 768? Yeah, 768. So it would cost you on average $15.18 to make 1 unit, but it only costs you $768 to make 2 units. And that's because as you make more and more units, that fixed cost has a less and less and less effect on the average cost. All right, B, find the marginal average. So we're finding C bar prime now. We're taking what we just got and doing its derivative. So that's d dx, I'll write out the fancy way, of 18x plus 1,500 over x. Now, I will say that since this is in the product and quotient rule section, you might think that, oh, okay, well, let me go ahead and do this with the product or quotient rule. That's fine, but it's also not the easiest way to do it. So I want to show you a special scenario here. Because the denominator is just x, it doesn't have x plus 5, it's not x squared minus something, it's just a single term. Because the bottom is single term, we can skip the quotient rule. So because the bottom is a single term, we can skip the quotient rule. I don't want to do that. Nope. So check this out. Before we go into the derivative stuff, 18x plus 1,500 over x. Let's split this up. You can only do this if the bottom has 1 term. If you go back to the previous examples where we did the quotient rule, 2 terms, got to do it. 2 terms, got to do it. But because this is 1 term, you can actually split this as 18x over x plus 1,500 over x. Then we can simplify. The x's cancel with the 18, so that's just 18 plus, and we know we're going to end up taking a derivative of this, so let's bring the x to the top. So that's 1,500 x to the negative 1. That was an x to the positive 1 in the bottom, so we make it a negative 1 in the top. So this is avoiding the quotient rule. Now it's just the power rule when we go to take the derivative. So C bar prime of x is the derivative of just 18 plus 1,500 x to the negative 1. The derivative of 18 is nothing. I'll write this 0 here for emphasis. Plus, then we have the 1,500, we leave that out front. We take the exponent down. So take the exponent down, and then the x is going to decrease by 1. Negative 1 minus 1 is negative 2, not 0. Negative 1 minus 1 is negative 2, not 0. Well, we don't need to write the 0 plus. The negative 1 times the 1,500 is negative 1,500. So that's negative 1,500 times x to the negative 2nd, but we generally don't like negative exponents of the answers, so that's negative 1500 over x to the positive 2. So the marginal average cost is negative 1500 over x squared. That's our marginal average cost. This is the function that tells us how the average is changing as we produce another unit and another unit and another unit. Now, the only variable we have is in the bottom. Now, the bigger x gets, the smaller this whole thing gets. If you take x equals 1, you get negative 1500. So that says that the average is dropping by like $1,500 to produce the second unit. Now, I've said before that these are not exact, these are approximations, especially early on, because that's not exactly true. We already talked about the average going from like 1,500 to 768. It was like 1,518 to 768. That didn't quite drop 1,500. So it's not a perfect predictor initially, but it's pretty good as you go further down the line. So part C was, find the marginal average cost at x equals 100 and interpret. Find the marginal average cost at x equals 100 and interpret. So what that means is we're going to plug in 100 here. So c bar prime of 100, which is negative 1,500 over 100 squared, which is negative 1,500 over a 1 with 4 zeros, just double the number of zeros. We can cancel 2 pairs of zeros, that's negative 15 over 100. We can divide both of those by 5, so that's negative 3 over 20. Or if you like the decimal, that would be negative 0.15. There's a fraction, there's a decimal. Doesn't matter which it is. What this states is the average cost to produce the 101st unit, the 101st unit, sorry, 101st book, instead of saying unit, let's be more specific, book or copy, is decreasing by 15 cents. But only for the 101st. If you do this at any different value, if you find the marginal average cost at, say, 10, so let's do a D, in fact. I don't normally do this, but I think this is important. Let's do C bar prime of 10. That would be negative 1,500 over 10 squared, which is negative 1,500 over 100, which is negative $15. So that would say the average cost to produce the 11th book is decreasing by $15. That's insane. When you're going from 10 to 11 books, your average cost is dropping from maybe 100 to 85, basically. I don't know the actual average cost. I'm not plugging that in. I'm just spitballing. So if the average cost to produce the 10th unit was $100, that says you can expect the average to do the 11th to be about 85. It should be 15 bucks lower. Yes, you're still paying a higher cost because if you make more books, you're paying more money, but the average is decreasing. And that is usually good for business because if you can produce more and have your average cost decrease per unit, that leaves you more room to make profit. It also leaves you room to drop the price of your item if demand slows down. So if your demand function decreases, if people don't want to pay as much, if you're producing a ton and the average cost is low to make more, then you can go ahead and make more and still have room for profit by maybe you produce 100 more units, you drop the price of your item by $1, and you could still be more profitable because of this decreasing average cost function. So as a business, this is definitely where you want to be. You want to see your marginal average cost be decreasing over time. This type of function, this rational function with x's in the bottom, this is where you want to be as a business. Now, they don't have to be polynomials and rationals. You can have radicals and all sorts of crazy stuff involved. But I'm just giving you an idea as to how you like things to flow in a real world sense. I'm going to point out one more thing and then we're going to call it a day. I always throw one of these on a test and students always have a difficult time with them. What they do is they just do a marginal. They don't do a marginal average. This is recorded. Please go back and watch this again and listen to me say this 10 or 100 times. A marginal average function is not just a marginal. It's not just an average. You got to do the average, then the marginal, which means derivative. If you just take the costs and do the derivative, if I ask for a marginal cost, that's fine. If I ask for a marginal average cost, it's completely wrong. And historically speaking, more than half of my students get it wrong, even after I warn them that on the first test, you would see one of these. So I am hoping that you will take this seriously and make sure you understand these slightly more complicated problems. I know, especially when you get with this funny notation, bars and primes, and it's a lot to keep track of. Practice makes perfect. Going back and taking notes again, rewatching things, studying the notes that you take, whatever you have to do is going to help. So we have finished section, I keep wanting to say 2.4 because that's my old book, which is where this example came from. There are good examples in our text as well for that, but I just really like that one, so I use it. So we have just finished 1.6.
And on that note, we are going to take our break. And like I said, I have to take a couple minutes off the break today, unfortunately, to be able to get the extra 2 minutes. The very last example that we're going to do today is very long. It's like a 15-minute example, and I don't want to cut class before that. So we're just going to do a 7-8 minute break. So we're going to come back at 7:58. So back at 7:58, and we will begin 1.7. So we'll see you then. All right, so we're going to go ahead and pick up in just a minute with 1.7. I did realize that I hadn't set the due dates in my math app for 1.4 and 1.5 for some reason, so those are set for today. I did set 1.6 for the 14th as well, and I know we'll finish 1.7 next time, so I went ahead and set that for the 21st, so I don't miss that. Right, so again, we have finished talking about the product and quotient rule for derivatives. Now we're going to get into what we call the chain rule in 1.7. And like I said, we'll be finishing right at the nick of time for tonight. So here we go.
Into 1.7. Lots of space. Chain rule. Okay, so the chain rule is for what we call composite functions. When we want to take a derivative of a function that feels like it has another function inside of it. So you've been through pre-calculus, you should all know what a composite function is. If you had me, I call it the chicken cordon bleu of math because it's one thing stuffed inside of another thing. But in math, it doesn't have to be chicken cordon bleu with ham stuffed and ham and cheese inside of chicken. You could actually go the other way and put the chicken inside of ham and cheese. You can also put chicken inside of chicken and ham and cheese inside of ham and cheese, because it doesn't matter how you compose functions. It's just what matters is that you can identify the composition and then do some stuff with it. So this is going to be, again, for functions where there's like an inside and an outside. So this, I thought I hit Control U. This is for taking the derivative of functions that look like they have insides and outsides. That's the way I like to kind of describe it vaguely. Like there's one function inside of another function, and you can see it. Now, I just want to put a few things to paper that I've said. Chain rule requires some composition knowledge. Given an f of x, g of x, compositions generally seen are fog, which is really read f of g of x. When I say fog or golf, I'm just being silly. F of g of x, and this is the composition notation, which honestly, I don't even know why mathematicians use it. I've never figured that out. Why not just do it this way, which is f bracket g of x? And the bracket could be an extra parentheses. So these brackets could be parentheses is what I'm saying. It's just the g of x is the inside function, the f of x is the outside function. So we'd be putting the g function inside of the f function. It's kind of like when you have f of 3, it tells you to plug 3 into the f function. This says we're plugging g into the f function, something more complicated. Or the other one that's very popular, GOF, g of f of x, which would be g bracket f of x. You can do f of f, you can do g of g, and that's what I was referring to with the ham and cheese and chicken. You can put chicken inside of chicken. You can put ham and cheese inside of ham and cheese. You don't have to put one inside of the other thing. You can have a pile of chickens, you can have a pile of other chickens, and you take pile or chicken 1 and put it in chicken 2. It's the weirdest chicken cordon bleu you'll ever have. It's like a turducken, but without getting different birds. But you could still do it, and I bet there's a chef that's done it somewhere. All right. So normally we focus in a pre-calc class on taking one function and stuffing it inside of the other, but we're going to take a different approach. So in pre-calc, we end up stuffing one function inside the other. But in calculus, we tend to focus on looking at one function and making it a composition, determining by determining inside and outside. So our goal is to write the original function as sum f bracket g parentheses of x. Bracket looks a little funny typed out. That looks a little better. Where what we call g of x is the inside and f of x the outside. Now, your original function may be written as f of x, so maybe you want to use different letters. Maybe use g and h and call g the outside and h the inside. It doesn't matter what you call what, as long as you have the idea sound. And there's a nice trick that I like to use. This is very helpful. When you're writing the outer function, place whatever would be the inside with x. Now, I wrote that as a capital X for emphasis. It doesn't have to be capital. It can be lowercase. I mean, a lowercase x looks exactly like an uppercase x, just smaller. So again, the trick is when you actually go to write what you're going to call the outside function, replace what you would call the, and I'm putting air quotes with my fingers, the inside with an x. Do I really have to have these quotes around inside and outside? Not really, but I just feel like because there are arguments for what the inside could be and arguments for what the outside could be, that I need to use those little air quotes. So before we actually get into the calculus side of things, let's practice looking at one function and turning it into a composition, finding out what these f and g's would be, because that's what we're really going to have to focus on the calculus side of things. And depending on who your pre-calc teacher was, you may have seen something like this before, you may not have. Depends on where you took the class and who your teacher was, like I said. So example 1. Given a function, I don't know why I'm handwriting this part now, but it's fine. Write it as the composition. In fact, I'm going to type it. Click, 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 click. Given a function, write it as the composition f of g of x. So for A, we're going to be given the function the square root of 2x plus 3. So there's our function, and we want to try and figure out what you would call the inside and what you would call the outside. And I think it's pretty easy to see what you'd call inside and outside based on this. The inside would be the inside of the square root, and the outside would be everything else, the actual square root itself. So the inside is the 2x plus 3. The outside, and now the inside is what we call the g of x, because that's what's inside the composition. The outside is the square root part. Now, some people will write square root and then they'll actually write the word inside here, but I don't really like to do that. I said that there's a pretty good trick with this, and this is especially important when we're getting to the calculus. When you're writing the outer function, which is what we're doing right now, replace whatever would have been the inside being the 2x plus 3 originally, instead of writing that 2x plus 3 where we identified it as the inside, just write it as an x. And I'm even going to use color for emphasis here. So that red x, the red x represents the inside. And I'll try and use the color for emphasis for a while. Because this red X, if you were to plug this inside, if you took this, which is the inside, if you plugged it into the variable of the outside function, you would end up getting the original function. And that's exactly the idea of a composition. It's taking one thing, putting it into another thing, all of its X's, and then you get something else. And the something else would be the original problem. So just for checking this, this is going to be the only one I check. This is literally going to be the only one I check. What is, and by the way, I forgot to write it, but the outside function is the f of x. Inside is g of x, outside is f of x. So if you were to do f of g of x, this is math you're supposed to know. Go back to the chapter R stuff if you're rusty and find the composition materials, but you plug the inside function in first. So we do f of, and the g of x, the inside was the 2x plus 3. So we're supposed to be taking f of 2x plus 3, which says we go to this function. So we're going to this function, but wherever we see an x, we're going to replace it with 2x plus 3. If this said f of 3, it would be the square root of 3. If this said f of 2, it would be square root of 2. But it's f of this thing, kind of like an f of x plus h, so we turn the x's into, instead of x plus h, well, 2x plus 3. So this would be the square root of, here's the square root from the outer function, from the f, and then instead of the red x, we write the inside of the f, 2x plus 3, which is exactly the original function. Now, here's the fun part, is that the original functions are generally denoted as an f of x. So instead of writing f and g, what you'll see me generally write are just the words inside and outside. Because if your original function is f, I can't call the inside or the outside f. I'd have to call them g and h. And there's nothing wrong with that, but a lot of people would instinctively write f. So I tend to write in and out. Okay, so let's do another one of these. B. Parentheses, 2x to the third plus 5x minus 3 raised to the 6th power. Same goal, write it as a composition. So we need to figure out what the inside function is, what the outside function is. So the inside and the outside with practice becomes a little more clear, but it's generally just looking for, okay, what's the complicated bits that could be separated as an in and an out? And it's generally the inside of a square root or the inside of a parentheses, or maybe the bottom of a fraction if the top is of a specific format sometimes. So what I would call is the inside of the parentheses, which the inside of the parentheses is the 2x cubed plus 5x minus 3. So that's what we call the g of x if our composition goes f of g. If I was doing g of h, then I'd call this the h of x. Making the outer function, the outside, well, that's the parentheses to the 6th part. So it's all of the inside raised to the 6th. But instead of writing the inside, you just write, and again, you could write it this. Some people would write, it's the inside stuff raised to the 6th power. But I don't like doing it that way. I like to use my little trick where I write an x representing the inside. So this red x, I feel like I have something extra here. This red x represents the original inside. It represents 2x cubed plus 5x minus 3. This is our outside function f of x. And if you put the black g of x inside this red x, you would very quickly get the original problem, the original function. Let's do a couple more. C, we got the cube root of x cubed plus 8 and then a -5 outside of the cube root. There's a little more going on with this one. Does that complicate what we would think the inside and outside are? In my opinion, no. But the outside function isn't going to be as simple as previously. So the inside, again, is typically insides of things being raised to a power, or square root, which is literally something raised to a power. Sometimes it's an entire denominator, depending on the format. Sometimes it's an entire numerator. It just depends. You could see these insides in multiple places. Maybe you only see them in one place and it complicates things. All right, so the inside, well, we've got this root, so I'd probably say the inside is the inside of that. So the inside is probably the x cubed plus 8. So that's what we would call our g of x. And then our outside is everything else. Just what we called the inside is now a red x, and you go back and you write the original function, but instead of writing the x cubed plus 8, just write the red x. So our outside function, it's the cube root of x, then a -5. See, the red x is representing this right here. The -5 still has to be there. It's not part of the inside. It's something completely outside of that. And if you were to stuff this x cubed minus 8 into the x here, you would get this original problem, this original function. Looks like a Madden drawing. Uno más, one more, por favor. Square root x plus 3 over x minus 6. So again, we've got a square root and there's a fraction inside of it. Now, whether that's acceptable or not in terms of algebra, we're not worried about. We're just worried about making this composition. So the inside is probably just the inside. I wouldn't call it just the top or just the bottom. I'd call it the whole inside. And again, I've said that there are times where you might call an inside the bottom of a fraction. That's not what's happening here. So the inside is the x plus 3 over the x minus 6, which we call our g of x, making the outside function the square root, but instead of writing any of the inside stuff, that's just a regular old x now. And that's what we call our f of x, which I did not write on the last one, but I did say it. This is absolutely critical to have as a skill. Otherwise, without the algebra, which is what this is, you can't do the calculus. Calculus is just formulas. That's all calculus is. Formulas and word problems. Hold on, I need a minute. Okay. Enough space? Yes, we do. So now that we understand how to write an inside and outside for a function that can be represented as a composition, even though it's not that way originally, we just say, hey, let's make it a composition. That leads us to the chain rule. The chain rule, this is used when a function can be considered as a composition. Key is finding the outside and insides, like above, given a function that could be represented as f of g of x. That is the key. So when you have a function that looks like a composition, so if I asked you to take the derivative of the square root of 2x plus 3, or if I asked you to take the derivative of any of these examples, it's not just a power rule, it's not a product rule, it's not a quotient rule necessarily. The D is a quotient rule, but it's also something else. A, you got the 2x plus 3 inside, so you think power rule, you got the square root, so you think power rule. because one thing is inside of another thing, it complicates things, kind of like a product complicates things, kind of like a quotient complicates things. When you have this outside and inside stuff, you have to chain derivatives. You're going to be doing what's known as a derivative of the outside and a derivative of the inside. So I'll write this out in plain English. The derivative of a composition is the derivative of the outside times the derivative of the inside. That's the chain rule. But this is a math class, so you know we're going to write it as a formula. So here we go. d dx of something. And that something is a composition. Now, because I'm putting brackets for the derivative, I just double parentheses the composition. It's not a real big deal. So the derivative of the outside looks like this. F prime of g of x. And I am going to use brackets this time. Since you wouldn't have a double bracket. This is the derivative of the outside, then times the derivative of the inside. That is not the composition O, that is a shaded O. Composition O's are like an open circle. So again, this is the derivative of the outside, the F prime part. And times this is the derivative of the inside. Now, when you actually go to take the derivative of the outside, you are going to do this kind of red X thing. You're going to use that to represent it. But when you actually go and show the answer, you're going to have to go and write what the inside is. So when you go through and try to do derivatives this way, I guarantee that you'll get way more answers right if you write what the inside and the outside are, show the derivatives of each, and then plug them into the formula. It's right here. And you got to memorize this formula. Like I said, we get a decent amount of formulas to memorize in here. Only a third of what a regular calculus class gets, but we do have to memorize a decent amount of formulas. So far, we've got the limit definition of the derivative, which we kind of shy away from for a while. Then we got the power rule plus its two special cases. Then we got the product and quotient rule, and now we have our chain rule. So again, this right here is our chain rule. We're chaining derivatives. We're multiplying a derivative of an outside times a derivative of an inside. Derivative of the outside times the derivative of the inside. Derivative of the outside times the derivative of the inside. That's the way I think about it. So when I do examples, I write what the inside is, what the outside is, what the derivative of each of those is, and then multiply. And that's it. So let's try it out. Not with red ink though, with black ink. Example, what are we up to? 2. Find the derivative. Given for A, and we're going to have this be 2x plus 3 in parentheses raised to the, 2x plus 7. Not that it matters that much if I had it wrong, but let's be consistent, and then cubed. 2x plus 7 cubed. So I just wrote the function. I didn't write f of x equals for this one, so I could call them f of x and g of x for the outside and inside. But I will start writing these as f of x equals or y equals. So it's a lot better just to write out the words outside and inside. Okay, so there's our original function. This is a composition because you've got stuff inside and stuff outside. It's not just 2x cubed, it's 2x plus 7 in parentheses cubed. If you wanted to do this derivative without a chain rule, you would have to multiply all this out. You'd have to take 2x plus 7 times 2x plus 7 times 2x plus 7. You'd FOIL, then you'd multiply that 6 product, then you'd do your power rules. Well, unfortunately, that won't work for every type of problem. While you can do it for this one, you can't do that for a square root. it would be very, very, very difficult to do it with b. And again, c and d you can't do it with. So we need to practice this idea of insides and outsides and then taking both derivatives. So the inside, I would call that the 2x plus 7. And again, I can call this the g if I want to, but I'm gonna avoid that. Then the outside, that would be the inside cube, but instead of writing the literal inside of 2x plus 7, that's where we replace what the inside function is with an x. That's showing that substitution. And then everything else, the parentheses cubed, but I don't really need the parentheses because now it's just x, so x cubed. I can wrap it in parentheses if I want, but it's unnecessary, so I don't. So that's our inside and outside. Now we need to take the derivatives of each of these things. So the inside derivative, that's me saying the derivative of the inside, or I could write d dx of inside. This would be another way, and I'm going to erase it in a second. I really wish my dog would stop barking. I don't know if y'all can hear that or not. So the derivative of the inside, well, the derivative of 2x is 2. Let me do this in blue. So the derivative of 2x is 2. That was a special case of the power rule. The derivative of 7 is 0. Again, special case of the power rule. Then the outside derivative this would be 3 times that x squared. And again, I'm going to leave that as a red x for now to show that that's a special variable that when we actually go to write the derivative, we're not going to be writing that red x. We're going to write what the inside is. So special memo. When you write the answer, the red x is really the inside, which in this case is 2x plus 7. Okay, so d dx of 2x plus 7 to the third power. We're finding the derivative, the slope function. The chain rule, it's the derivative of the outside times the derivative of the inside. Here's the derivative of the outside, which is the 3x squared. But I'm doing something wrong intentionally. I'm doing something wrong intentionally. As I just said, when you go to write your derivative, that red x should not be an x anymore. This is wrong. This should not have been there. Instead of writing the red x's, we're supposed to write what the inside is, which is 2x plus 7. So that's what I'm supposed to write. So again, instead of the red x, and I'll still write it in red, I write parentheses 2x plus 7. I need a parentheses because the 3 is a multiplier. And then the exponent was the 2. So again, this right here, this 3, then the red ink and the exponent is this right here. That's the derivative of the outside. But you don't write x for the outside bit. You write what the inside was, because this is just a small representation of it. Not a small, a temporary representation of it. That's what I meant to say. A representation for a small time. Okay, so that's the derivative of the outside. Then we have our times. And this next part is supposed to be the derivative of the inside. Derivative of the outside times derivative of the inside. The derivative of the inside, we just had 2, so we just write a 2. That's the calculus part. We've done the calculus. The algebra is clean this up as much as you can. There's a 3 and a 2 that are outside that can be multiplied. So that gives us a 6. That was the 3 times the 2. But the 2x plus 7 squared. There's nothing really necessary there. So that's our answer. Now, sure, you could take the 2x plus 7 and multiply it by itself and FOIL it and then distribute the 6. But here's the thing. The original problem was written with a parentheses and an exponent. We tend to like our answers in a similar format. So I would say this is a better format than expanding everything with all that extra multiplication. I'm not saying it would be wrong. I'm just saying this is likely a better format. So that was the problem. We figured out what to call the inside and the outside. When we labeled the outside, we labeled the inside as that red X. Then we took the derivative of each of those things, which was this and this, and then the derivative of the original is just the product of the derivative of the inside and the outside, but that red X that was representing the inside must actually go back to being the inside. It's kind of like when you do a substitution, when you go from dollars to yen. I don't want an answer in yen, I want to answer in dollars, so you got to go back to the dollar. And in fact, a couple of the homework problems actually take you through this process using a substitution instead. So I'll show you what I mean by that a little later, but for now, let's not throw too many methods at you all at once. Let's practice this method again. B. And let's have this one as y equals 5 parentheses 3x squared plus 2x minus 6. Close it and then raise it to the 9th power. Okay. So because we got stuff inside of other stuff, this is a composition. This is our chicken cordon bleu. It's best to label what the inside and the outside are. And then ultimately taking their derivatives. The inside is generally the inside of something. It's almost painfully obvious most times, but there's problems where it's not. It's going to be the 3x squared plus 2x minus 6. Which makes the outside everything else, but wherever you had the inside written, you're now just going to write it as an x. I like to have that color for emphasis, so it should be 5 times our x to the 9th power. I like the red for emphasis again. So the outside function, we're just calling 5x in the 9th, but I'm using the color to denote, hey, that red is really supposed to be something else in the long run. Now we just do each of these derivatives. I'll do them in blue. The derivative of the inside, well, the derivative of 3x squared is going to end up being 6x. You take the 2 out front, you multiply it by the 3. 2 times 3 is 6. You decrease the exponent by 1, and that gives you x to the first. You should all already be masters of the power rule. I can't emphasize that enough. Plus the derivative of 2x. And if you're not, go and do 2,000 of these. This is one of the special cases. The derivative of a linear term is just the coefficient, so that's a 2. Special case here as well, the derivative of a constant is 0. So the derivative of 3x squared plus 2x is 6x plus 2. For 5x to the 9th, its derivative, you'll bring the 9 out front and multiply. 9 times 5 is 45. And then we have our special red x, and it'll be raised to the 8th power. And again, when we're talking about the x, the outside function, that x really represents something else. So that derivative is 45x to the 8th. So the derivative of this thing, which because it's y, we can call it y prime, or we can call it dy over dx. It's the derivative of the inside, which is nice and normal, 6x plus 2. But we got to multiply this by something, so we should probably wrap it in parentheses, times the derivative of the inside. I'm sorry, outside. We just did the derivative of the inside. Pardon my misleading. So the derivative of the inside times the derivative of the outside. The derivative of the outside is this 45x to the 8th. So times 45, but not x to the 8th. This is wrong, this is wrong, this is wrong, this is wrong. Remember that in the outer function, the x represents the inner function. So that's supposed to be 3x squared plus 2x minus 6. That's what the x really represents. And then that's raised to the 8th power. And then this can be cleaned up. Now, this part being raised to the 8th power would be unseemly to have to multiply out. We generally are not going to do that. This is the point of the chain rule, so you don't have to do all these big products. However, this linear 6x plus 2 without an exponent is 45. That can be multiplied together, or you could leave them separated. The best thing to do is probably just leave the 45 in front. So very often you'll see it done this way: 45 times 6x plus 2 times the 3x squared plus 2x minus 6, and then raised to the 8th power. That is one acceptable answer. Oh, my cough made me mess up. But there are alternative answers. Your y prime. Because the 6 and the 2 have a common factor of 2, you could actually take that out and make this 90 times 3x plus 1 times that other parentheses, 3x squared plus 2x minus 6 to the 8th power. So again, what I did was I took a GCF of 2 out of the 6 and the 2 here. Because there's a GCF in these two, I can take it out because there's no exponent. I couldn't do that with the thing with an exponent. And 2 times 45 is 90. Or another alternative, if you distributed the 45 times 6, what's that, 270x plus 45 times 2 is 90. Now there's no number in front of the parentheses, it's been distributed in, and then the 3x squared plus 2x minus 6 raised to the 8th power. All 3 of those are acceptable answers, and my math lab should take all 3, and I would take all 3 on a test. Sometimes it's best to have the most factored version, which is the bottom left. This is the most factored. I would argue in many instances this is the best version, but really the one that I have boxed up, because taking out the extra factor of 2 generally doesn't do anything constructive, I'd say that one was just as good. I would say my least favorite's the bottom right. I would say this is my least favorite. But again, that doesn't mean it's wrong. It just means I like it less. And opinions are subjective, right? That it for that page, yes it is. All right, so let's do another one. See, and we'll actually write this one as f of x equals, so we definitely don't want to write the insides as f's and g's. So this is going to be 3 over the square root of 5x plus 9. Now, I see a square root, I see something in a bottom. There's a lot of things that are going to have to be cleaned up with this. So the inside function, there's a world where it could be the entire square root in the bottom, but it's not. It's just the inside of that square root. It's the 5x plus the 9. Making the outside function everything else, but when you go to write the inside function, just write it as an x. So 3 over square root of x, which represents the inside. Now, when we go to take the derivative of the outside, this is not in a good format. We need to clean this up. So that's 3 over x to the 1/2. This is going to get tedious. Which is 3 times x to the negative 1/2. This is the format we need to be able to take the derivative of the outside. Sorry, my dog's distracting me barking again. Sometimes I can talk over him, sometimes I can't. I'm easy to distract. So we needed this square root in a bottom, in the top, and with the rational exponent so that we can apply the power rule. We can't just take the derivative of 3 over square root of x unless you've memorized it, which admittedly I have, but I've done this 10 million times. All right, so now let's do the actual derivatives. The inside derivative of 5x would be 5. And the derivative of 9 would be 0. The outside's derivative, and again, we'll keep that x red to represent the inside the whole time. We bring the negative 1/2 out front. So that's 3 times negative 1/2. You could put the negative 1/2 in front if you wanted. And then there's our red x, representing the inside. And we're going to decrease its exponent by 1. And I've shown this before, negative 1/2 minus 1 is negative 3/2. I'll write that really, really quickly, and then I'm going to erase it because I don't want too much stuff jumbling up. Negative 1/2 minus 1 is negative 1/2 minus 2 over 2, which is negative 3/2. That's where that came from. LCDs, if you can't do that in here, I don't know how you're in calculus. Okay. Now, the original function was written with square roots and bottoms, so it's probably okay to go back to that type of notation. So that's what we'll ultimately do. You can do it now or you can do it later. Let's wait till later just to see both types of answers. So I'll hold on to switching this to the bottom and changing it back to a radical form. But now we can say that our derivative, f prime of x, or df dx, however you wish to write it, it's the derivative of the inside times the derivative of the outside. Well, and by the way, that negative 3/2, I should have cleaned that up. Darn it, that's negative 3/2 times x to the negative 3/2. Come on. Ugh, time consuming. Okay, derivative of the inside, that's the 5, times derivative of the outside, that's all of this. So times negative 3/2, then our special x, which really represents the inside being the 5x plus 9. So that's another parentheses, 5x plus 9, then that thing is raised to the negative 3/2. Well, the 5 times the negative 3 is a negative 15, so this is negative 15/2, and I can get rid of the blue parentheses. Then times the 5x plus 9, raised to the negative 3/2. Analytically, that answer is correct, but no one likes it in that format. We want to bring the negative exponent down to the bottom. So this will be negative 15 over 2 times parentheses 5x plus 9 raised to the positive 3/2. And then we want to switch to the radical notation, which gives us negative 15 over 2. The bottom of that exponent's a 2, so it's a square root, big old square root. The exponent's a 3, so that's the power. So inside we got a 5x plus 9 in parentheses raised to the 3rd. This is our derivative, and that's all we can do with it. It's technically not in an okay format because there's a square root in the bottom, but again, our class does not focus on that. This is okay to put in my math lab. It might even be okay with the rational exponents. I'm not saying, because I've seen my math lab accept a lot of answers, as well as turn down some answers I didn't expect. Practice makes perfect. But the moving of the -3/2 as an exponent down to the bottom and then changing to a radical, you could have done that up here. So the outside part, just note that that would have been, I don't want to write it there, I want to write it below. Note the outside derivative, if you had simplified, you would have gone from -3/2, then the red x to the -3/2. I'm going to skip the color changing for now. That would be -3/2 x to the +3/2, which would be -3/2 square root of x cubed. And that x would be red. I'll make them all red now. And you can see that the -3 is in here before we multiplied by the 5. The 2's in the bottom, square root's in the bottom, and there's the inside cube. So it did not matter when we simplified the rational exponent with its negative and all that jazz. We could have done it while we were describing the derivative of the outside, or we could have done it when we did the derivative of everything as a whole. Okay, so let's try another one. Do I have enough space? Yes, I do. Wrong color. Sorry, I'm just looking at something. I was trying to decide if I could make this one blue. Let me try that. Ooh, that looks really ugly. So yeah, I didn't think that would work. I'm just gonna have to keep switching colors. All right, D. F of x equals, silly me, f of x equals x to the 5th plus parentheses 1 minus x raised to the 5th power. This is where things start getting a little more interesting. So we're definitely going to step it up with the next couple of problems. And E is going to be even harder. F, you could argue is even harder, but I think E is probably the hardest one we'll do. This one is unique to the previous three because we're going to have to do the inside-outside stuff on the 1 minus x part, but not, but not on the x to the 5th. So this is a very unique type of function where you've got parts that you don't have to do the inside-outside with because this part is just a normal derivative, but then this part you do. So we don't worry about the in and out on the x to the 5th part, just the parentheses 1 minus x to the 5th part. So the way I'm going to write this out is that f prime of x is going to be the derivative of the thing on the right side, x to the 5th plus the parentheses 1 minus x to the 5th. I'm just taking expanded notation here because I know how to do the derivative of the x to the 5th. It's 5 times x to the 4th. So in blue, I'll show that derivative. It's 5. Wrong thing. The fact that I made that blue is making me want to click it now. Let's put it back to gray. Blue. So 5x to the 4th. That was this part. That's a normal derivative, no chaining necessary, no product, no quotient, just normal old power rule. But we can't do that for the other part, the d dx of the 1 minus x to the 5th. I haven't taken that derivative yet because we need to chain this part. We didn't have to chain the x to the fifth, so we took its derivative. We do have to chain the next part. So that's what we're going to focus on. That 5x to the fourth you're going to see in the final answer, it's just going to come back. But for the rest of this problem, when I'm doing insides and outsides, you're not going to see this guy anymore. I'm not completely erasing, I'm just saying that 5x to the fourth we're pausing on. So focusing on this, only focusing on this. The inside would be the 1 minus x, and the outside would be our x to the fifth, but we're going to use a red x instead to represent the inside. It's the inside to the fifth power. Then we can go and do their derivatives. The derivative of 1 is 0 because it's a constant. The derivative of negative x, there's a negative 1 implied to be there. And that's a linear term, so its derivative is the coefficient, which is negative 1. So the derivative of the inside is just the negative 1 because this thing has a slope of negative 1. For the outside part, its derivative would be 5x to the fourth. Drop the coefficient down, decrease the exponent by 1. So 5x to the fourth, but again, I'm still going to use that red x just for visual flair, saying that, hey, this is going to represent the inside function. Now we have the derivative of the inside and the outside. We can do our chain rule now. So f prime of x, the derivative of the original function. Now we can't forget this. A lot of students end up forgetting the blue 5x to the fourth. Remember the derivative, we were doing the derivative of the x to the fifth, which was this thing, no chaining necessary, so here it is. Then we have our plus. Now this next bit will be the derivative of what we did have to chain. So the derivative of the inside times the derivative of the outside, where the red x really is the inside. So plus negative 1, that's the derivative of the inside, times the derivative of the outside, that's the 5, then our x is really 1 minus x. Again, this x, we now write what the inside is. When you go to write the actual derivative, write what the actual inside is. And then that was supposed to be the fourth power. This can definitely be cleaned up. The 5x to the fourth in the front is just 5x to the fourth. The negative 1 times the 5 is a minus 5. And then you got your parentheses 1 minus x to the fourth power. That's all we really need to do. You could say, oh, there's a GCF of 5 between these two terms and pop it out. It doesn't really have a good effect, though. The only real okay alternative answer, which I just described, would be popping a 5 out of both of these terms and then having a bracket x to the fourth minus parentheses 1 minus x raised to the fourth. And I'll write that as df dx. Remember, f prime is df dx. It's the same thing. They're both acceptable answers. My math lab should take either of those. My personal opinion is that the top one is better. But again, that's an opinion. Opinions have a lot of variability. So this problem was unique to the previous three in that you didn't have to chain everything. There was just some pluses or minus, some terms that had simple things that didn't need an inside and outside. X to the fifth, power rule's okay. 1 minus x in parentheses raised to the fifth, you got to chain it because it's got an inside and an outside. The inside here is just x, so that's fine. All right, so let's step this up even more. I'm going to go ahead to the next page because I'm going to run out of room. I know I will. E. Let's now do f of x equals bracket parentheses x squared plus 1, close it, cube it, then a plus x, then close the bracket, and have that be to the third power. Okay. This is, in my opinion, the most complicated chain rule we'll do all day. Again, some people might argue that the next two, one of them could be more complicated by mixing a product in a chain rule or a quotient in a chain rule, but I really do feel like when it comes time to test, if I threw all 7 of these problems on the test, people could knock out the first 4, almost no one would get this one right, and more people would get the next 2 right. Well, there's definitely a chain rule going on. We've got this whole thing raised to a q power. But there's another problem going on here. It's bigger than that. So this right here is an inside, but also on the inside, there's another inside. There's another complication. You've got parentheses inside of parentheses. This is kind of like Inception. We've got nested compositions here. We put some cheese, wrap that up inside of the ham, then we wrap that up inside of the chicken, instead of just putting the cheese and ham inside of the chicken. So we put one thing inside of another thing inside of another thing. This is our turducken, our chicken inside of a turkey inside of a duck, or whatever the order is supposed to be. So this is a nested composition, which means we will need to chain this twice. So for the first layer, the first dive into the dream, I would call the inside everything inside of the bracket. The x squared plus 1 cubed plus x, and then I'd call the outside everything inside of the bracket cubed, the red x representing everything inside of the bracket. Now when we go to do the derivatives of these, when you go to take the derivative of the inside, you will need to chain this part. But then there's a plus, and the derivative of this x is a 1. So again, where I have chain and exclamation mark, I'm referring to this. We're going to have to do another inside and outside on that, but we're going to do that in a few minutes. So again, the part that's underlined will need to chain. So you're chaining a chain. It's like an f of g of h. There's an h function inside of a g function inside of an f function. For the derivative of the outside, though, everything's normal, thankfully. Drop the 3 out front, decrease the exponent by 1. I'm keeping my red x for emphasis that should be the original inside. So again, I'm even going to make a note here that this red x represents the original inside, which was the x squared plus 1 cubed, then plus another x. That's what that red x represents. And I want to change the color so it doesn't get too confusing. It feels weird saying x equals this thing because that can't be true, right? X can't be something more than x. But again, it's just showing a substitution that happens later. I also did not write the derivative for the outside part here. I wrote outside, not outside derivative. Make sure you write your derivatives. Outside is black, the blue is the outside derivative. So for now, we're going to pause. For now, f prime of x is going to be the derivative of the inside times the derivative of the outside. Well, the derivative of the inside is this thing that we don't know. It's whatever we have to chain plus the 1. So that's the derivative of the inside times the derivative of the outside. That's the 3. And then the x, which it represents, is this thing. x squared plus 1 cubed plus x. And that's supposed to be squared. So right now what we have is the derivative equals this thing, but there's an unknown here. We don't know what the derivative of the inside is. We haven't done it yet, so let's do that now. So let's pick a different color. Let's go with green. Let's find d dx of what we said we have to chain, the x squared plus 1 cubed. So for this one, we're going to call the inside the x squared plus 1, and its outside would be the inside cubed. If you don't like using x to represent that, you could also write the words in cubed, and then in the final thing, instead of writing in, write what the inside is. And by in, I mean the word in, not the letter in. So again, for emphasis, let's pick another color besides red. Let's go with pink. Close enough. So the outside is really that thing cubed. So now this feels like a whole new problem. We're doing this derivative. Here's its inside, here's its outside. Now let's do the derivatives of each of those. I'm going to stick with the green just because I've already got too many colors going around. The derivative of the inside would be 2x. The derivative of x squared, you bring the 2 down, and then you decrease the exponent by 1. I wonder if y'all can hear my dog panting. Dogs are fun. And then the derivative of 1 is 0. Then for the outside, the derivative of x cubed, you bring the 3 out front. And then that x is now going to be squared, but we'll stick with the hot pink to represent its inside function. So again, please note that the hot pink x is really representing the inside function, which was the x squared plus 1. So every time I write that hot pink, that's really what it is. Okay. So that says the derivative of the inner thing we had to chain is going to be the derivative of its inside, which is 2x, times the derivative of its outside, which is the 3x squared, but again, the magenta is really x squared plus 1, or the pink, whatever you want to call that color. And that's squared. The one thing we can do with this that's easy is the 2x times the 3 is 6x. So 6x times x squared plus 1 squared. This right here is what gets plugged in. Oh, this is going to get erased in just a second. Here, where it says chain exclamation mark. Because again, we didn't know that derivative initially, we had to chain it. Now that we have chained it, we can go back and fill it in. So we finally have f prime of x equals, we got the parentheses, the thing we got from chaining, which is this, the 6x squared times x squared plus 1 squared. I'm sorry, that's not 6x squared. It's 6x times the x squared plus 1 squared. So we have our parentheses, the thing we got from chaining, which was all this green, but then there's the plus 1 that was after that. This plus 1 is this plus 1 right here. Then we're going to close that parentheses. You could have made this outer parentheses bracket now if you wanted to. That would have been perfectly fine. Then the times 3 bracket parentheses x squared plus 1 cubed, then a plus x, and then all squared. Now, believe it or not, This is really all you can do with this. Again, I personally like this as a bracket instead of a parentheses. But it's this thing times this thing. There's no factors anywhere. There's definitely not any factors anywhere. So f prime of x, the only thing I want to clean up is this 3. Nobody wants a constant in the middle of two products. Put the 3 up front. So 3, bracket, then the 6x, then the parentheses, x squared plus 1, and then squared, and then another plus 1. Close the bracket. Then the other bracket, parentheses, x squared plus 1 cubed plus x. Close the bracket and square it. This is the answer. You might think that x squared plus 1 is a GCF. Well, it's here and here, but it's not next to this 1, it's not next to this x, and it complicates things because there's an exponent of 2 here as well. There is really nothing you can do here except multiply everything else together, which would be nightmare fuel. So we don't ask you to do that. Again, it is my personal opinion that that's the hardest problem in the section. I'm not saying it's the hardest, I'm saying my opinion is it's the hardest. Box it up. The reason it's the hardest is because of the inception thing going on. So we had the main inside, but that inside needed an inside and outside as well because it was a composition in part of it. So when we went to take a derivative, we were going to have to chain that, which we did in green below. The outside derivative was pretty normal. Outside derivatives are generally pretty normal because you end up boiling them down to just like a number times a variable with an exponent. That's the whole point. Your outside derivative should always be something clean and simple like this. You have to be very careful when you have parts that need to be chained and parts that don't. It's very easy to miss this plus 1. I will admit, when I taught this class, I want to say 2 or 3 years ago, I specifically remember this problem using it and forgetting my plus 1 in the answer. And then I went back and looked at my notes and I went, oh, darn it, I need to emphasize that to the students. I will never forget making that mistake. So again, there's a decent amount of algebra to keep up with this stuff. The calculus was really just a formula applied a couple of times. The algebra was understanding compositions. The algebra was understanding how to simplify things. The calculus was drop exponents down, label an inside and an outside. All right, that was E. Let's move on to F. Let's have this function be, why am I on red? Because that was the last thing I clicked, obviously. F of x is 2x plus 3 times 4x minus 7, but that one's squared. This is a product, so we'll need the product rule. One of the products has an inside and an outside, so we're going to need the chain rule. So this is both a product and a chain rule. The last one was chaining a chain, this one's product and chain. Spoilers, the one we'll do after this is the chain and the quotient rule. We're going to try all the different combinations. So we will need the chain and product rule. And I'm going to write the product rule that the derivative of some f times g, a first times a second thing. I'm going to write this the way I like to do things that's consistent with the quotient rule. I always go the second times the derivative of the first plus the first times the derivative of the second. This is the way I will always do my product rules moving forward. It's just my particular habit. As I've said, there's at least 8 different ways to do a product rule and get it right. The quotient rule, there's only like 2 or 3 ways to do it and get it right. There's less options because of the minus instead of the plus between them. Okay, so f prime of x. And I'll use these as first and second. It's going to be the second thing times the derivative of the first. So I'm calling the first bit the 2x plus 3, and I'm calling the second bit the 4x minus 7 squared. So my f is first, my g is second. If you want to go ahead and label out those derivatives, you can. Sorry for my coughing. Eraser. I want some more room here. I don't want to do that yet. I could have, but it's fine. So let me go ahead and show what these derivatives are. The derivative of the first, the derivative of 2x is 2. The derivative of 3 is 0. So that's the derivative of the first. And the derivative of the second, well, we're going to have to chain because of the inside and the outside. So I'll hold on to that for a minute. I don't want to chain it yet. I just want to show what our derivative looks like initially. So f prime of x for now, it's the second thing times the derivative of the first. So the second thing is the parentheses with the 4x minus 7 squared. So here's the second times the derivative of the first. So we're multiplying these two things, which is 2. Then plus the first, which is 2x plus 3, times the derivative of the second, which we don't know yet. We said we'll need to chain it. So maybe you write question mark, question mark, question mark, but I'm going to be a little more specific than that. This should be times the derivative of the 4x minus 7 squared. Darn my cough. And I think I tried to cough earlier. I tried to mute and then cough, and it's making me hit the button twice. So I may have coughed really loudly and then muted myself, but I saw it quickly and unmuted. So sorry if I coughed really loudly earlier. I feel it coming on. I try and avoid it. Anyways, so again, right here, all we've done so far is emphasize the product rule. Second times the derivative of the first plus the first times the derivative of the second. Again, the order of this is very, very, very open as long as you have a derivative times a regular function of the other thing. So the 2 in the parentheses 4x minus 7 squared could be last. I can put the 2 in front. I could put it after. I could put this parentheses after the derivative before. Like I said, 8, arguably 16 different ways this could be written out and be accurate. But now let's find out what this is. Now let's do the chain. So let's just focus on d dx of the 4x minus 7 squared. So we're going to need outsides and insides. The inside is the 4x minus 7. The outside is the inside being squared. The inside I represent with the x, the red x. You could write in squared if you prefer that notation. It's up to you. Doing these derivatives, the derivative of the inside is just 4. The derivative of 4x is 4. The derivative of 7 is 0. The derivative of the outside, you bring the 2 out front, decrease its exponent by 1. So it's 2x to the first power. I'll write the 1 for emphasis in the fancy 1 language. But again, you really don't write that 1 ever. So remember that red x is really the inside, which is 4x minus 7. That's what it represents. It's extremely important to remember not to write that as an x in the answer. So that 2x plus 3 that was in parentheses times the derivative, we can now do the derivative. This derivative would be the derivative of the inside times the derivative of the outside. So the derivative of the 4x minus 7 all squared is the derivative of the inside, which is the 4 right here, times the derivative of the outside, which is 2x, but don't write x, write the inside, which was 4x minus 7. Again, the 4 is the derivative of the inside. The 2 in the red ink is the derivative of the outside, but don't write x for the outside, write what it actually represents. And this, of course, can be simplified to 8 times 4x minus 7. Now, as you do these more and more, you may get to the point where you don't need to write what the inside and the outside are. You get more of a flow with this. You just kind of learn to take the exponent, drop it in front, leave the inside alone, and decrease the exponent of the inside by 1. Something like that. So finally, f prime of x. This 8 blah, 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 blah is this thing right here. Now we're able to finally have the derivative completed. So that derivative originally was, and I don't want to reorder things so you don't get confused, 4x minus 7 squared times the 2. That was the second times the derivative of the first, plus, here's the first, 2x plus 3, times the derivative of the second. So that's times what we just got of 8 times 4x minus 7. Clean it up. Put constants in front. So the 2 needs to go in front. So 2 parentheses, 4x minus 7 squared, then plus 8, put it in front. 8. And make sure you close the parentheses in front of, or after the 7. So 8 parentheses, 2x plus 3 times 4x minus 7. Now, maybe you can stop here. Honestly, no, this is not good enough. This is simplifiable. And you might say, well, man, that's a lot of different mess going on. Why is this simplifiable? Because look here, this factor, this term has 4x minus 7 as a factor. This term with the 8 has 4x minus 7 as a factor. There is a GCF this time. And I mentioned in the previous example, it felt like there might be, because you got this x squared plus 1 here and here, but it's not everywhere inside of the bracket. It's not everywhere inside of this bracket. So that wasn't a GCF, but this time it is. So usually what happens if we take GCFs out, we can make cleaner looking answers. This is not a very clean looking answer, and we can make it clean. So there's a GCF of parentheses 4x minus 7. It's here, there's 2 of them, but we're only going to take 1, and then it's here, there's 1, and we're going to take all of them. So let's take the GCF out. We're taking out the 4x minus 7. So we're taking this out, and we're going to open a bracket or a parentheses. There's a lot of parentheses, so probably a bracket. So we're taking one of these away from the thing with a 2 and the thing with an 8. There were 2 of them in the first term, which means now there's one of them left. So there's a 2, then a parentheses, and the 4x minus 7. So that was me taking the GCF from this bit. I haven't gotten to the 8 yet. Then there's the plus 8. The 2x plus 3 is still there. I'm not taking that away. I'm taking the 4x minus 7 away. So if I had 1 and I take it away, there's none left over. So this is taking a GCF out. The red parentheses will represent the GCF here. If you were to distribute this parentheses times 2 in that parentheses, you get a second one. Times the 8 in this parentheses, you'll get the 2 unique parentheses. Now what you can do is clean up the inside. And I'll put parentheses S there saying sometimes it's both insides, but really it's just the inside of the bracket. We can distribute the 2 and the 8. Because nothing can happen inside of the red one, it's just 4x minus 7. So bracket, 2 times 4x is 8x, 2 times negative 7 is negative 14. 8 times 2x is a plus 16x, 8 times 3 is a plus 24. Combine like terms. And we get f prime of x is 4x minus 7 times, and I really don't need that as a bracket, so I'll go back to a parentheses. 8x plus 16x is 24x. And then negative 14 plus 24 is a plus 10. This is a much prettier version of the answer. Generally speaking, when you have product and chain rules together, this happens, where you end up having a GCF that's like a binomial or something, and then you can clean up and clean up. Note that there is a GCF of 2 as well in the second parentheses. The 24 and the 10 have 2 in common. So really, you could take this one step further. If you prefer this to be as factored as possible, you'd have 2 times 4x minus 7. Now I'm taking the 2 from the second parentheses, not the 4x minus 7. So that's why I didn't change it. 24 divided by 2 is 12, so that's a 12x. 10 divided by 2 is 5, that's a plus 5. Both of these are good answers. I don't really think one's better than the other. I personally prefer the second version, but there's nothing wrong with the first version. It's more about preference. But if you had stopped way up here, this would not have been an acceptable answer on a test. Homework, it likely wouldn't take it either. It would say, well, while this is analytically correct, there is some simplifying you can do. Sometimes you get ugly answers because there's no GCFs, there's no fancy algebra you can do. Sometimes you get to a point you think you have an answer, but because there's stuff in common or like terms, blah, 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 then you can take it one step further, and you should in those instances.
And that is where we're going to end it, right on time. So like I said, we were going to start 1.7, but definitely not finish it. We'll do some more examples next time. And I think I actually accidentally label a second F. So be on the lookout for that. I'll double check. But yeah, so 1.4, 1.5 are due tonight. 1.6 is going to be due in a week since we finished that section. And as far as I am concerned, I believe we're supposed to finish 1.8 next week. It's tough to plan out an entire week of class all at once, but I think that's where we're going to end up. I will confirm that next week and give you dates and details for the couple of days that you'll have to take the exam and all that jazz. But for now, as always, if you have any more questions, you can shoot me an email. Good luck getting your homework done. Start studying for this test. Test problems should be comparable to homework problems, and you will get a review. So be on the lookout for that, and we'll talk about it next time. Have a good week, everyone. Take care.